All right. Hello, everyone. And on behalf of the Environmental Finance Center Network, welcome to not only our 18th session of our operator certification webinar series, but also part one to a two-part sub-series on solids handling. Today, we'll be focusing on mechanical solid separation. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics, and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that will include a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for the session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or if you need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, we can go ahead and get started. I would like to introduce our presenter for today, James Markham. James is a research engineer over at the Southwest Environmental Finance Center. Welcome, James, and I'll go ahead and hand it over to you.
All righty, let me get the right screen shared here. Okay. Let's try this again. What is going on? There we go.
Good, yeah.
Little time to react here. All right. Okay, thanks, Kristen. Thanks, everybody, for joining us. So today we're going to be talking about solids handling and wastewater treatment. It's a process that we kind of touched upon a bit in earlier webinars and kind of talked around, but we haven't really discussed in any detail. As Kristen pointed out, this is part one of a two-parter. Today we're going to look at the kinds of solids that get collected in wastewater treatment and cover mechanical solid separation. So essentially sludge thickening and mechanical dewatering. We'll look at some related math concepts and briefly introduce the topic of digestion. Part two, which my colleague AJ is going to present in 2 weeks on November 9th, mark your calendars, is going to be a much more in-depth review of aerobic and anaerobic digestion processes, some troubleshooting, and then the ultimate solids disposal options and requirements thereof. So definitely come back for part two. As always, given the kind of limited time that we have for these webinars, this is not going to be an exhaustive description of every permutation of these processes. It's really more an introductory sort of conceptual overview of the more common processes and equipment that you're likely to see, and it's designed to supplement your study of available resources from your state certifying agency and other resources like the Sacramento State Water Treatment Guides, which I highly recommend. So we're basically here trying to expose you to processes and types of equipment that you might not be familiar with or maybe don't have at your particular plant, but need to know about for an OPSERT test. And I also want to point out that although I'm going to be using some animations and videos and images developed by equipment manufacturers to demonstrate the mechanics of some of these processes, we are not endorsing any particular equipment, manufacturer, or process. These are examples for demonstration and explanation purposes only. So with that, let's set the stage with a little bit of review. Because as I said, we've talked about wastewater solids or different types of solids at a lot of points in this series. This diagram should look familiar, particularly if you were at our last sessions about activated sludge. Sort of a generic treatment diagram for a system with an activated sludge process. We've got influent coming in on the left, going through preliminary treatment, primary treatment, where we're collecting primary sludge, onto an aeration tank, secondary clarifier, where we're collecting activated sludge. Some of that goes back into the aeration tank as return activated sludge. Some of that gets wasted out as WAS. And then, of course, our clarified liquid goes on to either tertiary treatment or disinfection and ultimately out into the receiving waters. And we collect materials in a lot of different places here, starting with preliminary treatment, where we collect screenings and grit. And we talked about this pretty extensively in our session on preliminary treatment. We've got the coarse screening, so trash, sticks, other large debris that gets removed at the headworks with bar racks typically. The fine screenings, also typically shredded trash, larger inorganic materials, some organics that maybe aren't easily digestible, like bone and eggshells and coffee grounds. We covered different kinds of equipment that you can use for that, like what we're showing here, a mechanical step fine screen, but there's other options, wedge wires, perforated plates. We discussed grit removal there in simple grit channels, aerated grit chambers, cyclone separators, and the concept of grit washing and disposal. I'm pointing these out to specifically let you know that these are not the solids we're looking for, sort of to paraphrase Star Wars. When we're talking about solids handling in the context of wastewater treatment, this is not usually what we're talking about. And part of the reason for that is the grit and screenings have their own disposal paths. They're typically cleaned. The screenings either go to a landfill or get incinerated. The grit, mostly sand and gravel and other inorganic matter, it's also typically washed and sent to a landfill. And there's environmental regulations and permit requirements about that. So definitely check your local listings about what you have to do with that. And if you're unfamiliar with these processes, we did a webinar a couple of months ago about this. The solids that we're talking about in the context of solids management for these next two webinars, and generally when we're talking about solids management, are biosolids. It's basically the sludge. So this sort of deceptively small box in our diagram that includes solids handling and biosolids is dealing with all of the solids that get collected in the primary and secondary treatment processes here. So when I'm referring to solids handling in this webinar and in the next one, this is what we're talking about. It's the primary sludge that's coming out of our primary clarifiers. Again, we're using the primary clarifiers mostly for TSS removal, removing suspended solids. Tank shapes vary, but the principle is the same. We're essentially using gravity and engineering to get particulates to fall out of suspension so that we can collect them. And then we're talking about the WAS component of secondary clarifier sludge. Some of it goes back into the activated sludge tank. What we're not using is sludge that we have to deal with. And in this case, it's mostly biological flock and maybe some chemical flock if we're using chemical coagulation processes as well. I want to point out that the concentrations of solids in the WAS is typically much, much lower than primary sludge, but they both have to be dealt with because if you don't remove the sludge, the tanks fill up and your operations will cease to work efficiently. So now that we know which solids we're talking about and where they're coming from, let's talk about where they're going. Again, assuming everything is working correctly and to spec in your system, most of the suspended solids and dissolved organic solids are going to be taken out of your effluent by your processes before it gets discharged in the environment. And particularly for large systems, that's a lot of solids that get built up and have to get dealt with. And there's an additional way that these solids are different from the screenings and grit we deal with separately in preliminary treatment. And that's that the solids that we're dealing with in sludge are suspended in a lot of liquid. Remember, the sludge has to be processed further in this little box. So all of that primary sludge and waste activated sludge goes into a solids handling process that for this simple diagram is very basic, but actually in reality looks a little bit more like this. This is not the only setup that is possible. There are definitely variations on a theme depending on the kinds of solids you're dealing with and the volumes and what your processes are. But typically, primary and sludge and the WAS is going to go into some sort of thickening basin or process. Then it's going to move on to digestion, where we're going to basically do some more biological treatment, produce some biogas, which we may actually use in our processes. From there, it goes to dewatering. The effluent from that dewatering process typically gets recycled back into the plant for other uses, and then the solids that's left over get disposed of one way or another. And again, we're going to leave those that part of the equation for our next session. So we've got 4 basic stages that we have to think about when we're talking about solids handling. There's thickening, which is essentially reducing the volume of the sludge. There's the digestion, which is further breakdown of the sludge with microorganisms, essentially a continuation of what's going on in activated sludge, but with different goals sometimes. Then there's the dewatering process after digestion, where we're essentially removing more water from the solids, and then ultimately we've got disposal or reuse, which is the end of the line for the sludge. And there's a lot of different ways it can be dealt with. So as I said, there's many different options in each of these categories, but these 2 categories have a lot of similarities. So thickening and dewatering are essentially about volume reduction, and it's using mechanical processes to do that. So that's why we're focusing on what are essentially parts 1 and 3 of a 4-part process today, and leaving the digestion and reuse tomorrow till the November 9th session. So let's start talking about thickening, and it's just what it sounds like. It's reducing the volume of sludge that you're going to store in a digester. And this is typically step 1 after that initial solid separation process that's going on in our primary and secondary tanks. And there's many different ways it can be done: gravity thickeners, centrifuges, diffuse air flotation, various kinds of belts and presses. But before we get into the mechanics of how we do this, I want to talk a little bit about the why we do this. As I said, this is a little bit more of a conceptual webinar today. So why is thickening necessary? Well, basically because sludge is mostly water. Primary sludge is typically somewhere between 95 and 97% water and only 3 to 5% solids. So if you kind of do the math there, every pound of primary sludge is suspended in somewhere between 20 and 30 pounds of water. And on the secondary sludge, the ratios are even worse. You've got anywhere from 2 to significantly less than 1% solids in your secondary sludge. So at the extreme end of that, you could have a pound of secondary sludge solids suspended in 150 pounds, or roughly 18 gallons of water. So if you didn't remove all of that water, the digestion equipment in stage 2 of your solids handling process would have to be at least larger, if not huge. So one of the main reasons that we go through these thickening processes are to basically just reduce the mass of the stuff that we have to deal with in the later stages. And there's a lot of advantages to this. By reducing the concentration, increasing the concentration and reducing the water, we can improve digester performance. If we have to retrofit a digester to an existing system, the smaller we can make it, the less it's going to cost. And another aspect that's often overlooked is that digesters are biological processes, and depending on what time of year it is and where you are located in the country, you might have to heat that digester to get it to work efficiently. And then again, the smaller it is, the cheaper those heating costs are going to be. So that's sort of some conceptual side things. I'm going to walk you through a little bit of math to kind of really kind of nail home what's going on here. So if we've got a primary clarifier with 3,000 gallons of sludge that's producing a sludge concentration of 3%, we can figure out the weight of the solids pretty easily using a fairly simple formula, basically taking the sludge volume, multiplying it times the known weight per gallon of water, and then multiplying that by the solids concentration. 8.34 pounds per gallon is close enough for us to use in this situation. And if we run the math through, we can realize that our 3,000 gallons of sludge here, double checking to make sure that all of our units cancel out, is 751 pounds of dry solid sludge per day, which is pretty significant, but that's suspended in a relatively large volume of water. If we wanted to up that concentration, let's say to 5%, so we're dealing with the same amount of solids, we're just trying to concentrate it, what does that do to our sludge volume? Well, we can use the exact same formula, just rearranging it with our known weight and kind of work backwards to figure out what the volume would be. So we take our same formula, we plug in our knowns, and in this case, we're looking for sludge volume instead of the weight of the dry solids. We work our problem backwards, rearrange it, and we've got our same weight of solids per day that we're producing, but in a higher concentration, and our 3,000 gallons has been reduced to 1,800 gallons per day. So we've kind of done mathematically here what we talked about earlier. And what this kind of shows is that small increases in sludge concentration can result in relatively large decreases in sludge volume, which is what we're looking for our next stage of sludge treatment. So, small decrease in solids concentration percentage, significant decrease in sludge volume. You may be able to get the appropriate concentration of solids in your primary clarifier. You're probably not in your secondary clarifier, but you have to maintain each of those processes' operational parameters within the parameters that they're designed for. So, you may want to have thicker sludge coming out of there, but it might not be operationally possible. And that's why you might need a thickener as an intermediate step between those sludge production processes and the digestion processes. So again, we just did mathematically what's going on in the thickening process, increasing concentration. So now that we know sort of the what and the why, let's get into the how. And I'm going to start with gravity thickeners because they're one of the more common versions of these that we see, and also because it uses a process that you should be very familiar with if you were at earlier sessions, because it uses a sedimentation process. It's essentially a different kind of clarifier with some slight tweaks to it that has operated with slightly different operational parameters. It works on sedimentation. We did an entire webinar on sedimentation processes that I highly recommend you take a look at. But essentially what we're doing, we're slowing the effluent velocity down. We're using flocculants and gravity to settle those solids out. Using clever engineering. And if you weren't at the last webinar, I kind of think of flocculated settling as an analogy to snowfall. If you think about a snowstorm up high, the flakes are separate, they fall, they clump together, they get bigger, they fall faster, eventually they land on the ground, and as they pile up, they kind of start to act as a unit because they pack together and they compress the snow beneath it. So that's essentially what's going on a conceptual basis inside a gravity thickener. If you want to see what one of these things looks like and you've got a snow globe at home, shake it up and take a look at what happens, and we'll give you kind of a good idea. The components of a gravity thickener are really similar to what you see in another kind of clarifier. You've got an inlet distributor assembly, typically in the center. Effluent gets pumped in. You've got a baffle that slows it down, that extends down into the surface of the water so that the solids start moving in the right direction. You've got a sludge rake on the bottom that's slowly rotating around, moving sludge that deposits on the bottom of the thickener into a hopper where it can be withdrawn. Those rakes typically have pickets on them, so little fingers sticking up. Those are there for a couple of reasons. It helps with the flocculation because as it's slowly stirring, it's letting those flocks bang together and form larger flocks. It also helps release trapped gases that may develop in the sludge. Gases developing in the sludge are going to counteract settling. In bad cases, they can actually cause the sludge blanket to rise up in the system, which is the exact opposite of what you want to do. Again, we're using gravity here to push the flock down to the bottom. And it also helps limit the amount of scum that forms on the surface, which can be a cause of odors and attract nuisance insects. And that is, a potential issue of a poorly run thickener. You can have a lot of scum develop on it. If you've got gasification going on, they can develop odors. So they have to be maintained pretty well. So let's talk a little bit about some of the operational factors that come into play. Again, mostly on a conceptual level, sludge type is going to matter. The age of this feed sludge will matter. The temperature of the sludge that you're dealing with will matter. So remember when we talked about sedimentation, there are seasonal changes that you have to deal with. Obviously, the sludge blanket depth is going to impact performance. How much solids you're holding in the tank for how long, which are essentially your solids detention time, but also hydraulic detention time and hydraulic loading are also going to play a factor. We covered how to calculate detention time and hydraulic loading in a math-specific webinar earlier in the series, so I'm not going to go over those formulas today, but just recognize that these, like your other clarifiers, are parameters that you have to understand and know how to work with. And if you're not familiar with how to calculate those, I highly recommend checking out the earlier webinar. But again, these are also all covered in your state and other resources available. So let's talk a little bit about sludge. So gravity thickening works best with primary sludge, typically because it's relatively high concentrations of solids in there. Fresh sludge typically can be concentrated to the highest degree, and part of the reason for that is that old sludge can get septic. If it gets septic, those anaerobic and facultative bacteria that may be living in there start to strip out oxygen and produce things like methane and hydrogen sulfide and carbon dioxide, which form bubbles that get trapped in the blanket because it is kind of it's not solid, but it's semi-solid and can lift some or all of it up. You can theoretically use gravity settling for secondary sludge, but it settles much slower because it's a lot less dense. Another reason it settles slower is that remember that the secondary sludge solids are mostly biosolids, so it's microbes, and they are 85 to 90% water, and that water is trapped inside the cells. So it makes the settling go a lot slower, and those solids in secondary clarification processes are also typically a lot finer, so they settle slower. This is why, as we'll see in a little bit, particularly in smaller plants, quite often these two streams are merged together. So your primary sludge and your WAS get merged together to go into a single gravity separator, one that cuts down the cost of having two, but also it makes the secondary sludge settling work better. Sludge age is also an issue, so that's going to be related to your detention time, how long it's been sitting in there, how old it was when it came out of the primary and secondary clarifiers to begin with. Again, if you hold the sludge too long, what dissolved oxygen is in there might get depleted. You can actually run into situations where you've got denitrification going on in the bottom of your tank, and a little bit might be okay, but a lot, again, can result in gasification, bubbles form, raising your sludge blanket. Another issue that you might run into is an abundance of filamentous organisms. We talked about those in the activated sludge webinar. And old sludge tends to have more of them in there. Temperature, again, another important factor to think about because there's still biological activity going on in here, and as sludge temperature rises, so does the biological activity, which is just another way of talking about some of the things we've already talked about, which is gasification and sludge rising. So this is why typically you will have higher sludge rates, removal rates out of your thickeners in the summer versus the winter, because you're basically offsetting those increase and decreases in biological activity that's going on in the bottom. So there are a lot of different designs of these. So I'm just going to give you some sort of general operational guidelines. There's many more factors that you need to think about other than loading and thickening percentages. There are manuals like the SAC state books that I talked about, and your state guides that will have the required information in them, and your operation manuals for your particular system will tell you the ranges that you're supposed to be working in. But typically, primary sludge solids loading rates are somewhere in the 20 to 30 pounds per day per square foot range, and the output sludge is about 8 to 10% solids. Activated sludge, on the other hand, has much lower loading rates and consequently much lower thickened sludge solids percentages. And that kind of makes sense if you think about it. Most of your solids are coming out in primary treatment. a smaller volume of solids is coming out in that activated sludge process in your secondary clarifiers. We talked about trickling filters during our fixed film webinar. So if you need some information about those, check that out. But trickling filters also produce biosolids that have to be dealt with, and they kind of fall somewhere in between the primary sludge and activated sludge, both in terms of operational loading rates and the thickened sludge that comes out. As I mentioned earlier, quite often WAS streams and primary streams are combined into a single thickener, and as you can see there, you end up with a combined sludge loading rates and thickening percentages, solids percentages, somewhere in between primary sludge and activated sludge by themselves. Another thing that you'll have to pay attention to, again, is hydraulic loading rates. Not going to go over the calculation. We covered that in an earlier webinar, but I'm going to give you some typical ranges. So, hydraulic loading rates in gallons per day per square foot for primary sludge in the 400 to 800 range, activated sludge typically about a quarter of that, and combined streams sort of fall in the middle. You may have to mess with the hydraulic loading rates to make your system operate the way you want to. And one of the ways that that gets done is by blending secondary effluent with the sludge that's going into the thickener. And in addition to sort of increasing the loading rates, one of the things that can also do is help prevent septic conditions and odors from developing, because you're essentially adding cleaner, more oxygenated water in there. So with that, we're going to get to our first poll question. It was a bit of a conceptual question based on the things that I've been talking about. So Kristen, if you want to throw that up there. Basically, if you've got a gravity thickener and you're experiencing gasification and sludge rising, which of the following options might help correct that? So increasing sludge wasting to lower the sludge blanket depth, decreasing the sludge wasting to increase the sludge blanket depth, increasing secondary effluent recirculation into the thickener, or decreasing secondary effluent recirculation into the thickener. And I will point out that there are two right answers here. So we'll give you about a minute to think this out, and then we'll walk through what the correct answers are and how we get there.
All right, it looks like most people have their answers in. So go ahead, I'll give everyone about 10 more seconds and then I'll close this poll.
All right, most of you got this right. Yeah, so our two correct answers here are increasing sludge wasting to lower blanket depth, or increasing secondary effluent recirculation into the thickener. And this is a little bit of a connect the dots kind of thing, so I'm going to walk through this. So gasification, as I mentioned, is often a result of septic sludge. Septic sludge is often the result of extensive sludge retention time. So if you increase the sludge wasting to lower the blanket, you're essentially removing sludge at a faster rate, which is shortening the sludge retention time. So that's one way that you can deal with that. Increasing the flow of secondary effluent going into the thickener is another way that you can potentially help freshen sludge. Those aren't the only two options here, but of the options that I presented, those are the likely go-to scenarios that you would want to approach. The net result of either of those is going to be a decrease in the concentration of solids in the sludge that you're taking out, but typically an improvement in the effluent quality, which is what you're going to look for. I said we were going to talk about a little bit of math. One of the parameters surrounding sludge detention time, and blanket depth is what's referred to as the sludge volume ratio, which is just the ratio of the sludge blanket volume divided by the volume of sludge that you're pumping out of the thickener. And I want to be clear that when I say sludge blanket volume, I'm not referring to just the solids in there. I'm referring to the entire sludge blanket. So if you got a round thickener, it's the depth of the sludge, with your pi r squared formula to figure out the volume of that part. SV ratios are typically between 0.5 and 2, but there are design variations. Typically, for higher maximum concentrations, you're going to use a higher SV ratio, and lower values are going to be used during warmer weather. So again, if more sludge enters than leaves, the blanket volume increases. If more sludge leaves than enters, the volume decreases. So we've got our second little poll question here. Do the setup for you. We've got a sludge blanket volume of 28,200 gallons. Sludge flow into the thickener at 100 GPM at 3%. Sludge flow out of the thickener at 40 GPM at 7% concentration. What's the SV ratio? Everything you need except for a simple conversion factor is there. So remember, your SV ratio is in days and your flow is in minutes, so you're going to have to convert that. So take about a minute and see if you can come up with an SV ratio for this particular problem. I'll see you on the other side.
All right, go ahead and get those answers in. I'll be closing the poll in 3, 2.
All right, the answer here is actually half of a day. I will walk you through the math here to explain this. And I will point out that I did put a couple of red herrings in here just to make your life a little more difficult, but I'm trying to make a point with this. So to calculate this, what we need to know is the sludge blanket volume, which I've given you as 28,200 gallons. And then we have to figure out the volume of sludge that's getting pumped per day. So what's going out of the thickener is 40 GPM. Which we have to convert in to gallons per day. So we have to use our 1440 minutes per day factor to convert that, which basically ends up with 28,200 over 57,600, which gives us a half a day. So I wanted to point out a couple of things. One, I simplified part of this problem and I made part of it more complicated than it needed to be, because this is often the kinds of things that you might see on a test. Sludge blanket volume, again, I gave you here on an OPSERT test. You're often going to have to calculate that. They'll tell you what the sludge depth is. And then again, you'll have to use your pi r squared or pi over 4 times diameter squared formulas to figure that volume out. The other thing to point out is that in the context of this particular question, concentration does not matter. So if you picked one, you probably actually flipped the ratio upside down. Instead of dividing the volume by the volume of the blanket by the volume of sludge, if you flip that equation upside down, you ended up getting 1. So just make sure that you're putting the right things in the right places. If you picked 7, you actually probably multiplied that concentration of the output in the bottom line, which threw you off. And this is kind of a good idea, why it's a good idea to have flashcards. We talked about that I think in the very first webinar in this series about study methods. Having flashcards or drumming sort of typical ranges for common parameters into your head can be a pain, but it's sometimes useful because it will help you potentially weed out incorrect answers. So as I mentioned before, SV ratios typically somewhere between 0.5 and 2. So 7 is kind of far outside of that range. So if you got a really high number for this calculation and you knew the range was somewhere between 1/2 and 2 days, that would potentially make you sort of rethink your math and double check your math. The other thing to point out is that quite often you'll get a set of information that applies to multiple questions. So the question we're going to do here in a second actually uses the concentration components. So you have to be very careful about making sure you grab the right formula and the right parameters or values that are given to you to plug into that formula. This is, again, one of those parameters that you're going to use. It's going to vary based on the design. So, if you have one of these systems, it's really good to understand what your engineers decided your system parameter should be, what range it's supposed to be in, so that you can dial in that accordingly. Another parameter that you're often going to look at with thickeners is similar to the parameter that you look at with other kinds of clarifiers, which is removal efficiency. So we've got another problem here, and in this case, the concentration does matter. And this is just a typical efficiency formula where you're looking at, in this case, not the sludge going out, but the influent in, so the sludge coming in and the effluent out. So in this case, we've got 30 GPM going in to a thickener at a 3% concentration, which is 30,000 milligrams per liter, and an effluent flow out of the thickener at 0.15% concentration, which is 1,500 milligrams per liter. So take those numbers, throw them into that formula, and see if you can come up with the removal efficiency for this set of particular parameters. And Kristen, if you want to throw the answers up there.
All right, go ahead and get your answers in. I'll be closing the poll in just about 10 seconds.
Awesome. Yeah, most of you got it right. It's 95%. Just to show you the math real quick. So basically what we're taking is the concentration of the input minus the concentration of the output times 100, dividing that by the concentration of the influent, and we end up with 95%. On a problem like this, they might in the exam give you a numerical concentration without giving you the milligrams per liter, or vice versa. You can actually do it both ways. So if you didn't know what the milligrams per liter were, you could simply just take 3 minus 1.5 divided by 3 times 100 and get to the exact same number. If you have to do the calculations to turn a concentration into milligrams per liter, because they might give you 1 in percent and 1 in milligrams per liter. Just remember that there are 1 million milligrams in a liter, so 3% concentration would be 0.03 times 1 million, which would equal 30,000. So you can just basically move the decimal places there. So Solids removal efficiency is another thing that you're going to keep track of as you do this. And again, your particular system will have design parameters that you're trying to hit. So that's a lot of information just about gravity thickeners. There are other methods to do the same sort of process, and we'll talk a little bit about them as well. And again, there are a lot more parameters that you're going to have to keep track of, but as I said, this is meant to be sort of more of a conceptual overview. Other thickening methods that typically get used or DAF, which is dispersed air flotation, centrifuges, belts for filtration, and drums. I'm going to start with flotation because it's kind of the exact opposite of the gravity process we talked about just now. In gravity thickening, we're using physics to push the solids to the bottom of the tank where we can collect them. In a flotation process, we're using physics to push the solids to the top of the tank. And it's kind of a neat process. This is a cross section of what a DAF unit typically looks like. And you'll have sludge and polymer coming in at one end, usually at the bottom, and it gets mixed together and released into the basin. And part of that sludge feed is air bubbles, which causes the sludge to cling to the outside edge of the bubbles and rise up, where this mechanism at the top, which is essentially a bunch of brakes, scraper blades, that rotate, slowly move the sludge off the top to one end where it can be discharged, while the clarified effluent, which you can see going out the bottom down here under a weir, goes out the other end. So it's same net effect as gravity separation, but we're working in the opposite direction. Although, of course, some sludge is always going to settle to the bottom. So every DAF unit I've ever seen or read about has a bottom sludge collector for the little bit that ends up down there. And I do want to point out that they can be round like regular clarifiers, or they can be rectangular like what I'm showing you here. Flotation is used in a lot of different industries, wastewater, food manufacturing, mining, all sorts of things. And there's a lot of different ways that it can be done. You can use dispersed air flotation, where you're generating bubbles using mixers or diffused aerators. You can use biological flotation, which is essentially just letting the gases that biological activity creates to float the solids. You can use what's called dissolved air vacuum flotation, where you're essentially aerating the effluent at atmospheric pressure and then putting it under a vacuum, which causes bubbles to get released. Or you can use the more typical process that's used in wastewater, which is dissolved air pressure flotation. And in that case, you're essentially aerating the effluent under pressure and releasing it to atmospheric pressure. And the mechanism that's at play here, every one of us has seen, even if you don't know it. It's exactly what happens when you open up a can of soda. The liquid inside the soda can has gas dissolved in it, and it's under pressure. And when you crack the seal, you're basically exposing it to atmospheric pressure, and the air, or in this case of the soda can, the CO2 that's dissolved in the liquid effervesces out. It basically forms bubbles and comes out because of that pressure change. And so that resulting foam you get is, what happens when a liquid that's saturated with gas under pressure is released to atmospheric pressure. It's also somewhat similar to what you see the divers have to deal with. So the deeper they go, the more nitrogen gas that's in their bloodstream gets dissolved into the bloodstream. And if they ascend very, very quickly, so if the pressure changes very quickly, those bubbles, that dissolved nitrogen gas actually bubbles out in your blood and causes the bends. So same physics going on, but in the case of wastewater treatment, we're essentially using the creation of those bubbles to float solids to the material, because the solids stick to the outside surface of the bubbles. There's three different sort of typical flotation methods that get used: full flow, partial flow, and recycled flow pressure flotation. In a full flow system, you basically are pressurizing the entire stream of influent flow before you release it into the DAF unit. In a partial flow flotation setup, you're pressurizing some of the influent flow that is released into the DAF unit, and some of the sludge just goes directly in, and the two mix inside the unit and float the solids. But the more typical version that you see is what's called a recycled flow pressure flotation. And that's where we essentially take effluent that's coming out of the system or from another location in the facility. We pressurize that and release it into the DAF stream. So it's kind of like, you know, opening up a can of soda, you know, underwater and watching what happens. You know, the bubbles form, they go up through the liquid that they're in and float whatever's in there to the surface. This is a schematic of a typical recycled flow setup. So you've got your flotation unit, you've got effluent coming out of it that gets recirculated. That effluent gets mixed with an air feed and it goes into an air saturation tank where it's typically boosted up to somewhere between 45 and 70 PSI. If you don't have mixers in there, you can get saturation levels of around 50%. There are typically mixers in these because if you've got a mixer in there, you can actually get the air saturation up to around 90%. And the detention time is going to vary depending on the design. It could be anywhere from as short as 30 seconds to as long as 30 minutes, depending on what kind of setup you've got. But that saturated air liquid solution goes through a pressure reducing valve and gets introduced into the sludge feed as it's moving into the flotation unit. So effectively, like I said, you're opening that can of Coke in the sludge feed line, the bubbles form, and as they form, they rise the solids in there to the surface, and it looks something like this. This is the top end of a DAF machine. Where you can see that rather thick foamy sludge blanket on the top, and you can see the flights of scrapers there moving the sludge off the top into a hopper where it's moving on to its next process. And in just a second, you'll see the other end of the machine where it shows the very clear effluent going out, some of which is going to be recycled, some of which is probably just going to go up to the front end and move through the entire system again. So that's what one of these things looks like in practical terms. They vary in size, they vary in shape. This again happens to be a rectangular one. There are round ones as well. There are a lot of different designs, so there are a lot of different parameters you have to pay attention to. One of them is the air solids ratio, which is kind of unique to this particular situation. And this is a technically unitless ratio where you're tracking the amount of air versus the amount of solids that you're putting in to the DAF unit. If you've got 100 gallons per minute of WAS with a concentration of 9,000 milligrams per liter going into your DAF unit, and you're moving air in there at 5 cubic feet per minute, you can figure out the AS ratio. And again, the ratio that your particular system is designed for will be given to you. By doing something like this. The key to knowing this is knowing the density of air. So we've got a flow of air, 5 cubic feet per minute. There are tables that you can use to look up the density of air, 0.75 pounds per cubic feet. So for every 5 cubic feet of air, we've got, that weighs 0.375 pounds. Using the same formula we used in our earlier calculation to figure out the solids amount in the ratio, or in the stream, we've got 100 GPM, 8.34 pounds per gallon times 9%. That gives us 7.5 pounds of solids. So we've got air to solids ratio of 0.005. We can double check our math, make sure all the units cancel. Technically, the pounds cancel too. As I said, ratios are always unitless, but this is commonly referred to as pounds of air over pounds of solids. So I've left that in there. The right range, again, is going to depend on the sludge type, the unit design. So I'm not going to give you like a typical range for this like we did with some of the other parameters. But typically, you're going to need a higher AS ratio for more concentrated or heavier sludge. There are some operational guidelines that I can talk about, and those relate to what you can do with polymers and what you can do without. So you often use polymers in DAF processes, not always, but you can sort of see what the differences are here. You know, the minimum influent solids concentration is going to be the same. Same thing with the air solids ratios. Those ranges are the same as are the recycle rates, or the amount of water we're moving back through that air feed. But you can get significantly higher solids loading rates if you're using polymer, and slightly higher hydraulic loading rates if you're using polymer, because it just helps that bubbling, sticking action, raising everything to the surface. Also, polymers give you significantly higher solids recovery rates. DAF units, like everything else, have some issues that you might have to deal with. Typically, what you're looking at is you know, the thickness or thinness of the float blanket and the quality of the effluent coming out. If your float blanket is too thick, one of the things that you might do is check the solids loading, maybe lower the float rate, or increase the speed of those scrapers that's moving across the top. Those can all be controlled independently. Same line on the other side. If you got a float blanket that's just too thin, you might slow the flight speed down so that more is allowed to build up there. And then, you know, depending on what's going on with your float, you might have to look at your AS ratio, look at the air input, look at compressors, because you know, you're relying on that pressure differential here. So if your compressors aren't working right, or the cycle times are incorrect, or the loading's excessive, you may run into operational problems. But again, if you've got a system like this, you should have an operations manual. And if you grab those SAC state books or look at your state materials, they will lay out the basic information, troubleshooting information that you're going to be responsible for on a test. There are also centrifuges that we use for this process. And if you've ever seen a washer, you've seen a centrifuge at work. Basically, it's analogous to the spin cycle in your washer with some fancy engineering. And just like washers, there are centrifuges that spin on a horizontal axis and some that spin on a vertical axis. I've got a couple of videos I'm going to show you here really quickly. This shows a solid bowl centrifuge at work. This is one of the more typical versions that you'll see in a wastewater treatment plant. Actually, they're probably the most widely. They're continuous feed processes. We've got a horizontal bowl that's kind of in a cone shape that rotates on its axis at really high speed, typically somewhere between 400 and 1,000 RPMs. And inside the bowl, there's a rotating screw conveyor that is moving in the same direction as the bowl, but at a lower speed. And as you'll see here in a second, sludge gets fed through the inside of the unit and comes out of that rotor somewhere in the middle, and the centripetal force of these spinning components basically forces the sludge out to the outside through the liquid pool, where it gets compacted along the outside edges, and then the screw moves the solids toward one end, which you can see splatting out on the right-hand side of the page, while the liquid goes out the other end. So net effect is you've got solids settling through that pool of liquid, getting compacted and being conveyed where it exits as thickened sludge, while the centrate, or the liquid that's been centrifuged out and it's left out, exits the unit at the other end. There are also basket centrifuges that work along somewhat similar principles, but in a different direction. These are typically used in batch processes. And they spin on a vertical axis, and essentially sludge gets pumped into the middle. They spin around at very, very high speeds. The sludge gets compacted against the outside edges. It's that brown layer that you can see right there. And after a certain point, that builds up to sort of a required thickness. A sprayer, which you can see there on the left-hand page, will sort of wash off the loose sludge. And then that compacted sludge is scraped off the inside with a plow or blade that basically pops up. That's what you're seeing on the right-hand side. Scrapes that cake off, it drops out, and the whole process starts all over again. So similar concept, slightly different mechanics. We also have belt thickeners. These are derivatives of belt presses that are used for dewatering. With this option, we're essentially using gravity and a porous belt to, whoops. Come on now. All right, my video is not working here. I apologize for that. But basically what we have is, there we go. Polymer and sludge being fed into one end, distributed along a belt. And as you'll see, That belt has little plows in it that create furrows, which basically enable the free water to drain out through the bottom of the belt. The sludge goes across the top. It gets collected at one end. The liquid flows through the porous belts out the bottom and is collected and dealt with. So this is kind of those plows at work. And basically, by creating the furrows, it's concentrating the sludge and providing the water additional paths to drop out of the bottom of the belt. There are a lot of different designs of these. You can, again, used in a lot of different industries. There are different belts with different porosities depending on the kind of sludge you're dealing with and how thick it is. These really work very, very well. Typically in size, they range from maybe 3 to 10 feet in width. And then, as you can see there, the sludge gets collected at one end and goes out in a hopper and moves on to our next operation, which is digestion. There are also drum thickeners, and as you see these videos, you'll realize they're all just variations on a theme, different ways to get water out of the sludge. So with a drum thickener, slightly different setup. You've got an angled porous drum that is rotating, typically at a much slower speed than the centrifuges. Again, typically there's polymer added at the input stage. That polymer and sludge gets mixed together, it helps the solids bind. And then as it moves through the drum thickener, that drum thickener spins around in circles along a almost vertical axis. Water drains out through the bottom, through the porous outside edge, and the plates inside essentially convey the increasingly dewatered sludge from one end to the other, where it gets dumped out and moves on to the next process. And we'll see that here in just a second as our little sludge gate here opens up. So you can see they turn relatively slowly here, because again, we're basically letting gravity do all the work. With a centrifuge, we're adding energy to spin the water out. Here, gravity's doing most of the work. So a bunch of different kinds of thickeners. Here's kind of a brief table to compare sort of the types that they're used for and how often they're used. Gravity thickeners typically used for either untreated primary sludge or a combined flow of primary and WAS. Theoretically, you can do it for WAS by itself, but it isn't done very much because it does a poor job of concentrating the solids. DAF units, they're not typically used for both streams. They're more common just for WAS, but they're expensive to run. So their use is decreasing over time. And then the other kinds that we showed here are typically used for WAS, typically in large to medium plants, and they all have pretty good solids concentration. Of course, the next step is digestion, but as I said, we're skipping that because that's going to be the topic of our next webinar. And you're probably wondering, I talked about thickening and digestion, and here we are almost at the end of the webinar, and I haven't talked about dewatering yet. And that's because dewatering uses a lot of the same processes. So it's all about vacuum reduction. We use some of the same kinds of techniques to do it. One option is a vacuum drum filter, which is kind of like the last thing we saw, but in reverse. Instead of the sludge going on the inside, the sludge is going on the outside. And you'll see a cross section here. Basically, the sludge and polymer goes into the bottom of the tank. This spinning drum has a vacuum in the middle, so it sucks up liquid. The solids stick. It sucks the liquid out as it turns, and on the other side of its rotation, the now dewatered cake gets scraped off. The main difference between thickening and dewatering is in dewatering, you've got much, much more dry solids. Belt filter presses. This is one you've probably seen in other videos of ours. It's one down in Texas. Come in a variety of sizes. And basically, as I said, the gravity filter belt for thickening is just a derivative of this. And if you look at this particular unit, the part that's in the middle of the page is actually a thickening belt setup followed by a press setup. And the main difference between these is that in a belt press, you've got 2 belts instead of just 1, and you're using gravity in the first place to dewater, and then you're squeezing those solids between 2 porous belts through a bunch of rollers to get the rest of the water out, or most of the rest of the water out. These are really, really common. They're all over the place. This one happens to be in Antarctica because they have to deal with wastewater down there too, and you can see the plows sort of in the gravity dewatering process, and then the rollers are underneath. So this is what one of these looks like in action. Quick video, same sort of process. Polymer being added at the beginning to help with the dewatering process. It's distributed over the belt. In this case, we've got kind of a 2-stage process where we've got what's effectively a thickener at the top. And this part of the process looks exactly like what we've looked at before. And then after this gravity thickening piece, you will see that the resultant thicker sludge gets squeezed between a set of belts and a set of rollers so that we can get a much, much drier cake as a result. So here we can see sort of the bottom end gets dropped on a belt. You can see it wedging, and then it runs off to a different set of rollers. And they vary in size. There may be 3, 4, 5, 12, 15 rollers, depending on how big your system is. The net result is, in addition to letting gravity pull free water out, we're using that squeezing action between the 2 bolts to essentially wring what's left of the water out of the system and give ourselves a bunch of dry cake at the end, which we can then use in the disposal. There are other technologies that I'm not really going to talk about. They are variations on a theme. There's screw presses that look like this, essentially rotary mechanisms that work slightly differently but do the same thing, essentially using squeezing action to squeeze the water out. But we also use solid bowl centrifuges and basket centrifuges for the dewatering stage as well. So you might actually have the same kinds of equipment at the dewatering stage as you had earlier on in the process at the thickening stage. You're just operating them at different parameters to get drier cake at the end. So again, same concept, slightly different output, basically thicker solids concentration. So with that, our time is up. I apologize, I went over a minute or two. We'll open the floor to any questions if there are any. And in the meantime, I want to point out that we are still available for office hours. Tuesday to Thursday, excuse me, on Tuesday between 9 and 10 Pacific, noon and 1 Eastern. But you can always reach out to us at any other time. And the funding that provides this webinar series also provides technical assistance. And I do want to point out that technical assistance can include helping you with your OpCert exam tutoring. If there's a concept you don't understand or formulas that you can't wrap your head around, we're happy to talk to you about them as well. So don't think of this office hours as just necessarily technical assistance for plant operations. If you're having trouble passing the exam, maybe need some help on a particular area that you're having difficulty with, or need some study materials, again, feel free to reach out to us. We are happy to assist. We're your tax dollars at work. We're funded by the EPA to do this. So with that, AJ has joined us. He's our kind of resident expert on all of these things, although I know quite a bit as well. So let's see if we got any questions we can answer.
I'm not currently seeing any questions in the chat.
Awesome.
Yeah, there's no questions quite yet, but feel free to go ahead and get those questions in if anyone has them. In the meantime, I just want to remind everyone that after this webinar that you are able to complete a webinar evaluation. We really value whenever each of you fills that out, because we take your ideas and it helps us plan for future webinars. So please take the time and fill that out. Also, following this webinar, each of you will receive a follow-up email, and that will include links from the slides from today, as well as a link to the recording. And let's see, we have a couple things coming in. What is your preference between a belt press or a centrifuge?
It's really going to be design specific. They both accomplish the same thing. So, that's really kind of an engineering question. I'm not sure what the operational cost differences are. Maybe AJ, you could weigh in here. But really, both of them do the same function. It really is kind of a matter of footprint and energy use and what you need. I will point out that centrifuges are kind of designed for continuous use. They're a continuous flow process, whereas belt presses in smaller systems are often only used a few times a day. Or excuse me, a few times a week. That one belt press that I showed you from our friends down in Gatesville, they run that a couple of times a week. So they basically, withdraw sludge from their thickeners on a schedule and fire up the machine, dewater, dispose of, turn it back off. Which is maybe a little bit more difficult to do with centrifuges. Any other thoughts, AJ?
Yeah, I would say that centrifuges are more often used in like larger volume plants with more biosolids. Belt presses tend to be a little more energy efficient. However, that's if you're using like one. But if you need to do the same volume, you're going to end up creating more of a footprint. Like you said, you're going to have to use more. One centrifuge might do the work of like 3 or 4 belt presses. So you can do them with a smaller area. And they can process more solids. But it's going to depend on the plant. If you have a smaller plant, a belt press would be more desirable because you're only going to have a belt press for the amount of solids that you need, and then you're not going to have the energy usage that the centrifuge would have.
Anything else?
Great. And then I don't see any other questions. Couple of comments that this was great, excellent presentation. And one more question just came in. Which polymer works best for dewatering, an ionic or cationic?
That is not a question I can answer. AJ, do you happen to know the answer to that? I guess some of it is going to have to do with the kind of solids that you're dealing with.
Off the top of my head, I don't know. There is an answer though. I know that for dewatering, there is specifically, I don't remember if it's anionic or cationic though. I'm gonna do a quick Google search and see what it tells me, because there is one is better than the other, because you're not supposed to use one for dewatering, and it has to do with the type of solids.
While AJ is looking that up, I do want to point out, if anything occurs to you after this webinar is over and after we close the Q&A, you're welcome, like I said, to just reach out by email to us with any questions you have. And if we can't figure out the answer right away, we'll look it up and get back to you.
It looks like I'm seeing cationic, and I believe that's because after the dewatering process, I think after like the digestion process, the sludge is more acidic, if I'm correct. So the sludge is anionic, so you want to use cationic to bond those anionic acids that are going to be more, or like because they're more acidic, if I remember correctly.
So it sounds like there might be sort of a general rule, but might be some variation on the theme depending on exactly how your digestion process is working.
Yeah, and then for any polymer usage, you're always going to want to perform bench tests to make sure that you can optimize your polymer.
Right. Anything else, Kristen?
Yes, we have one more. Of all the types of equipment mentioned today, which uses the least amount of energy during operation?
Probably a belt press, because you basically only have to use it when you need it, whereas some of the other ones are kind of designed to be going all the time. That would be my initial thought on that. But of course, your energy use and your thickening and dewatering requirements are going to kind of be plant dependent. So, and also footprint dependent, as AJ pointed out, depending on the size of your plant. If you had a very big plant, even though an individual belt press might be technically, on a unit per unit basis cheaper to run, it might not have the efficiency that you need for the amount of solids that you're dealing with. So you kind of have to look at the cost and energy use relative to what you're trying to accomplish. And that's definitely something that would be worked out, in an engineering process, or if you've got a CIP that you're working on to develop a new plant or expand a plant. That is definitely something to consider. And that is a really good discussion to have with the engineers that you're working with, because engineers quite often are used to building things a certain way for certain parameters. And so asking questions like that can really help make sure that you get the appropriately sized equipment for what you need. Because again, there's the cost of constructing a facility and the cost of running a facility. So, you may end up in a situation where you've been working with a belt press that's relatively inexpensive to run, but maybe you're dealing with more solids, and it might make economical sense to switch to something that maybe costs a little bit more to run, but is more efficient, like a centrifuge. And I do want to point out that, with the centrifuges, there are different kinds that we pointed out. There's the bowl centrifuges, which are generally continuous flow. The basket centrifuges, those are typically batch processes. So those work to some extent a little bit like a belt filter press, in that you basically turn it on when you need it and turn it off when you don't. So again, like many things in the wastewater world, it's situations vary, but that is a really good question to ask, particularly if you're in the process of redesigning your setup or designing a new setup.
We also got a similar question. John is looking for the equipment that uses the least amount of energy while providing efficient functioning for a small municipality, about 500 to 5,000 residents, if you have any recommendations for that.
I would say that we probably need a little bit more information for that. So John, if you wouldn't mind reaching out to one of us via email, so we can get a little bit more specific information about your system, the volumes that are going through that, we might be able to do some math and come up with that. But again, I don't want to give you sort of a short answer, not knowing all of the factors in place. Probably not the answer you were looking for, but I think you'll get a better answer in the end if we go that route.
Perfect. And that is all of the questions that we have. Thank you, James and AJ, for your time today and for sharing your expertise with us. As I mentioned previously, please fill out the webinar evaluation. We really appreciate when you take the time to respond to those. And thanks to each of you for attending today. We hope to see you at future EFCN events. Thanks, everyone.
Thank you. Thank you.